Assalamu alaikum. Welcome to your third lecture in Principles of Computer Networks. In this lecture, we will discuss the physical layer. We will have an introduction to the physical layer. We will cover guided transmission media, wireless transmission, and communication satellites. The physical layer is the first and lowest layer of OSI reference model and of our hybrid model. Its function is to transport data through electrical, mechanical, or procedural interfaces. It determines how to use electricity or light or electromagnetic waves to transmit data, raw data from layer 2 into the communication media. That's to say, a wire like a twisted pair or fiber, or even wirelessly through electromagnetic waves. The physical layer performs a variety of functions, amongst defining the bit in terms of voltage and length, defines the data rate, that's to say the speed that the data flows from source to destination, and to ensure that the sender and the receiver are synchronized. It also defines the transmission mode, whether it was simplex in one direction only, half duplex in both directions but not simultaneously, full duplex that data is transmitted in both directions simultaneously. It also determined how the devices are connected to the transmission medium through interfaces like Ethernet or radio waves. It has point-to-point configuration and multi-point configuration. It converts data into electromagnetic waves upon sending, and from electromagnetic waves to digital data upon receiving. This is what we call modulation and demodulation. It also sends the data packets from one port to another port physically, and that's what we call switching. When the data is sent over physical medium, it needs to be converted into electromagnetic signals. The data itself can be analog, such as human voice, or digital, such as a file on the disk. Both analog and digital data can be represented in digital and analog signals. Digital signals are discrete by nature, and they are represented in pulses of electricity or pulses of light. Analog signals are continuous wave by nature and represented in continuous electromagnetic wave. As you can see, digital signals can be converted into analog signals and vice versa. The transmission on physical medium can be weakened. This weakness can be due to a number of things. First, attenuation, that when the signal passes through a medium, it tends to get weaker. The longer the distance is, it loses its strength. For the receiver to interpret the data correctly, it needs a stronger signal. Dispersion. The signal travels through the media. It tends to spread and to overlap. This creates a dispersion, and the dispersion depends upon the frequency used. Delay distortion. When the signal is sent over a media, it's sent with predefined speed and frequency. If the speed and frequency does not match, this might cause some bits to be delayed, and the bits will be received in an order that it was not sent. For example, for digital media, this is very critical. Some bits have to reach the destination in the same order it was sent. The last cause of weakening the transmission is noise. Noise is known as a random disturbance or fluctuation in analog or digital signals, and it might happen for a number of reasons. It can be thermal noise due to heat, or intermodulation noise due to multiple frequencies sharing the same medium, or crosstalk when the noise that happens when two mediums are passing near each other, and it can be impulses from irregular distribution of lightning, electricity, or short circuits. The channel capacity is the speed of transmission of information. It depends on three main factors: the bandwidth, that's the physical limitation of the underlying media; the error rate, the incorrect reception of information because of the noise; and the encoding, the number of levels used for signaling. Modulation and demodulation are the processes of converting digital signal into analog signal at the source and digital signal to analog signals to digital signals at the destination. While multiplexing is a technique to mix, send multiple data streams over a single medium. There are multiple types of multiplexing: frequency division multiplexing, time division multiplexing, wavelength division multiplexing, code division multiplexing, and space division multiplexing. This is the subject, and with modulation and demodulation are the subject of your writing assignment for this week. For multiplexing to happen, there should be a multiplexer that is hardware, a physical layer device that takes multiple signals and multiplex it in a single transmission channel. And at the destination, there is a demultiplexer that takes the incoming signals and demultiplex it to several signals as it was from the beginning. There are two types of transmission media: guided media, that's to say wires, and like copper wires or fiber optics, and unguided media, that's to say wirelessly, like radio and lasers. In this part of the lecture, we will cover the guided transmission media. We will cover magnetic media, twisted pairs, coaxial cables, power lines, and fiber optics. Magnetic media, we mean by that magnetic tapes or removable media, like discs. The process is pretty simple. You write on the magnetic tape or removable media. You transport the tape or the discs to the destination machine, either from one office to another, or across town, or even across the country. When the data reaches its destination, you just read the tape or the removable media, and that's it. It has two main advantages. Bandwidth. A tape contains up to 800 gigabits. A box can hold up to 1,000 tapes. That is 800 terabits per box. We can actually send multiple boxes, hundreds of boxes at a time. Sorry. As for the cost, a tape costs around $40. That's $4,000 per box, plus $1,000 for transportation. It's probably much less. That is $5,000 per box, which leads to $6.25 per terabyte. This bandwidth and this cost cannot be beaten by any other computer network. So why do we need computer networks? Because the earlier way of transmission has tremendous delay that runs from minutes from one office to another, to hours across the town, to days across a continent. And there are communication applications that needs much faster response time in terms of seconds or milliseconds. Hence, computer networks. The first and the oldest and the most common is the twisted pair. The twisted pair is a twisted pair of insulated copper wires. They're twisted to reduce the interference. The twisted pair can be used for transmitting either analog or digital data. It's adequate and its cost is very low. But as the wires extend, the signal becomes weaker. That's why we need repeaters. A repeater is a device that extends the distance between signal source and signal destination by amplifying the signal. It's very simple. It's a physical layer device that takes a weak signal, amplify it, and resend it. There are 4 types of twisted pairs. They were usually 7 types. Now the existing are 3 types. Category 3 is no longer existing. The one which is in use now is category 5 and category 6. Category 7 is not in use yet. Category 5 transmit from 100 megabit per second to 100 to 1 gigabit per second. Category 6 transmit up to 10 gigabit per second. Category 3, 5, and 6 are all called unshielded twisted pair, while category 7 is a shielded twisted pair, and you should read more about this. The difference between category 3 and category 5 is in how many twists are there in the pair. Apparently, as you can see, category 5 twists are much more than category 3 twists. That led to better signal transmission, less interference, and higher bandwidth. That's why category 3 was replaced by category 5 in all telephone networks. Category 5 twisted pair has 4 twisted pairs, where in Ethernet 100 megabit, 2 pairs only are used, 1 for each direction, and for 1 gigabit Ethernet, we will find that the 4 pairs are used in both directions simultaneously. The next to study is the coaxial cable, or the coax as it's called. It consists of a stiff copper core surrounded by an insulating material. The insulator is encased in a woven mesh of a conductor. The outer conductor is covered with protective plastic. There are 2 types of coaxial cables. 50 ohms, that's for digital transmission only. 75 ohms, that's for analog and digital transmission. It has much higher bandwidth than the twisted pair, and excellent noise immunity. It was used widely for long distance lines, in cable TVs, and in WAN internet over cables. It's not much in use now. Another form of guided transmission media is power lines, where power lines have been used by electricity company for sending and receiving low rate bit data, such as remote metering and home control and controlling home appliances. In recent years, there has been a renewed interest in using power lines to transmit data simultaneously for broadband networks or for home LANs. The idea is very simple, where the frequency of the power signal is different than the frequency of the data signal, so they both can be multiplexed in the power line. And you plug your smart TV, and then you will have both electricity and connectivity. The problem is now there are various standards in terms of products, electrical products, and there is no international standards. People are working towards this. Another guided transmission media is fiber optics. Fiber optics is a technology that transmits information as pulses of light through a fiber out of glass or plastic, mostly glass. The core cable is a glass fiber. Another glass layer is called cladding surrounding the core fiber, and it's enclosed in a plastic jacket. Fiber optics cable can have from one fiber up to a few hundred fibers. As you can see here, this is a side view of a single fiber where there is in the middle the glass core and the cladding glass and the plastic jacket. Multiple fibers can be enclosed in one cable that as I've said, can contain from few fibers into up to few hundred fibers. Fiber optics transmit data in form of light particles or photons. They pulse through the fiber optic cable. The glass fiber optic cable and the cladding have different reflection indices. That means the light reflects differently from each one of them. This is very important because this is used to create a total internal reflection. That means to trap the light within the fiber. The fiber signals don't travel at the speed of light because of the density of the glass, and it can go slower than by around 30%. As we can see here, how the total internal reflection happens. The reflective index of the material and the angle with which the light hits the surface together decides how much of the light is reflected or in what direction the light is reflected. So with certain angle, the light will be completely trapped in the cable. Fiber optics cables can be deployed either by laying in the ground within a meter in depth, or buried in trenches near the shore, or lie in the bottom of deep water of the sea. The connection between two fiber optics can be through fiber sockets, and that is the cheapest, the fastest, and the most maintainable. But the amount of loss of light is high. It can be also spliced mechanically, this for the two fibers to be laid down next to each other and enclosed in a plastic cover. Or it can be fused together, and this is the nearest for having one extended cable with the least amount of loss in light, but this is the most expensive. The detection happens through a semiconductor device with a positive and negative junction that converts photons or light into electrical current. This device is called a photoid, and it has a response time of 1 nanosecond, which limits the data rate to about 100 megabit per second. The optical transmission system consists of light source, LED or laser, transmission medium, fiber optic cable, detector converting the detected light to electrical pulses. The propagation mode can be multi-mode or single mode. As we can see here, this is an example for optical transmission system where the input data from digital format comes into the transmitter circuitry that transmit the data to the light source. The light source will transform the data into light pulses, on for 1, off for 0. The detector will, on the other end of the fiber optic cable, will receive the pulses of light, and we convert them into digital data, 1 for on and 0 for off. That's to say 1 for presence of light and 0 for absence of light. The guided transmission media in fiber optics has to do with the performance, has to do with the source of light itself. The source of light can be LED or semiconductor laser. For LED, the technology costs less and has longer lifetime, has minor sensitivity to temperature, but it has lower data rate and works in only multi-mode and has shorter distance. While the semiconductor laser has higher data rate, it works in multi-mode and single mode, it goes for longer distances, but it has shorter life, and it is affected substantially by temperature, and it's really expensive. If we compare fiber optics to copper wire, we will find that fiber optics has higher bandwidths, lesser attenuation. That means lesser repeaters are needed, about 1 every 50 kilometers for fiber optics and 1 every 5 kilometers for copper. It's noise resistance, no interference, no power shocks, and it's thin and lightweight. That means lesser transportation costs, and it has excellent security. The wire tapping is harder than tapping a copper wire. The cons that fiber optics interfaces costs more, it's fragile, and we have untrained personnel who don't know how to deal with fiber optics. See you in next part.